Hey everyone, this is Dr. Walker. In this video, I'd like to go over example of 570 number 2 on dipole energy. Even though this example is going to be really easy, I wanted to go over it because I didn't have a video for the slide on the energy of a magnetic dipole in our notes. So hopefully you didn't miss out on that slide. What we saw in the slide is that a magnetic dipole in a uniform magnetic field is going to have to store potential energy, and it's going to be the dot product, the negative dot product of mu dot B. And this should look very similar because we saw when we had electric dipoles that they stored energy as well, and the energy they stored was negative P dot E. So both the electric and the magnetic dipole, they want to rotate when placed in electric fields and magnetic fields respectively. So that means they're going to be storing energy when they are in those fields. This example says that we have a wire formed into a circle. We're given the diameter and it's in a uniform magnetic field carrying a current. We want to find the range of potential energies of the wire field system for different orientations of the circle. So we're not given the orientation of the loop of the magnetic field. So I just drew a random loop with the current going clockwise as viewed from above. And let's just pretend that the magnetic field is going down. It doesn't matter because we're just looking for the minimum and maximum energies. And we know that the minimum energy, as we saw in the notes, the minimum energy is negative mu B. And this happens when the magnetic moment is parallel to B. We know that the direction of the magnetic moment in this case, if our fingers are curling clockwise as viewed from above, the thumb is down, so the magnetic moment is going down. So when they're parallel like this is when it stores the minimum energy. And then all we need to do is plug and chug the NIAB here, for NIA for mu and then B. And N is equal to 1 because it's just one circle. We have the current, which is 5. We need the area, so we know that the radius is half of the diameter, which is going to be 5 centimeters or 0.05 meters. And then the area is going to be pi r squared. That's going to give us 0.00785 meters squared. So now we just plug and chug the numbers. Negative 1 times 5 times 0.00785. The magnetic field is 3 milliteslas. Milli is 10 to the negative 3. So 0.003 teslas. And we're going to get negative 1.18 times 10 to the negative 4 joules. And then the maximum energy is going to be mu B, and this happens when the magnetic field is going the other way and the angle between mu and B is 180 degrees because the cosine of 180 gives us negative 1, cancels out this negative. So it's going to be the same exact number, just positive. So I just want to go over this problem just to practice using this equation and to just be able to say a little bit more about it since I didn't have a video, that your magnetic dipole, just like your electric dipole, is storing energy when it is placed in that external field.